Hello everyone. First of all, I'm going to talk about the exercise we did. So the exercise is that calculate unsigned 6-bit integers 47 divided by 5 using optimized division algorithm and also original division algorithm. So here is the solution. The first one is the original division algorithm, and the second form is the optimized division algorithm. So one important thing is that since we are trying to do the division on 6-bit integers, therefore the quotient register should be 6-bit, but divisor and remainder registers should be 12 bits. So recall the hardware design for this original division hardware. If the quotient is 32 bits, then the divisor and remainder should double the size. So in this case, if the quotient is 6-bit, because we are trying to do division on 6-bit integers, then the divisor and remainder should double the size. Similarly, in the optimized division algorithm, the divisor is 6-bit, but the remainder and quotient register should be 12 bits. And after you figure out the bits of each register, then you can first initial the values and then follow the algorithm and then get the final result. So basically the final result here should be the same. And for the original division method, we get a quotient is 1001 and remainder is 10. And for the optimized division algorithm, we get quotient is 1001 and also the remainder is 10. So recall that the left side of the remainder register is the remainder and the right side of this register represents quotient. I will also post this file to Blackboard. Next, I'm going to talk about signed divisions. When we are trying to do division on signed numbers, so the simplest solution is to remember the signs of the divisor and dividend, and then negate the quotient if the sign disagrees. But the question is, what is the sign of the remainder? Recall that we talked about this division before, so dividend equal to quotient times divisor plus remainder. And in this example, if we try and divide 7 by 2, then clearly the quotient should be 3 and remainder is 1. And all those numbers are positive. And we can apply that to this format. The dividend equal to quotient times divisor plus remainder, which is 3 times 2 plus 1, and the result is 7. So what if we want divide -7 by +2? And well, the quotient should be 3, remainder should be 1, but what is the sign of those two numbers? So for example, if the quotient is -3 and remainder is +1, so is this correct? We can also apply those to this equation. So if we apply it, then we get -3 times 4 plus 1. Then the result is -5. This is not correct, right? So the result should be -7, but instead we get -5. What about this one? So the correct one should be this. The quotient is -3 and the remainder is -1. And then if we apply that to this format, then it will be -3 times 2 minus 1. And then we get -7, which is the correct dividend. What about +7 divided by -2? Then the answer should be quotient is -3 and remainder is +1. So based on this analysis, we can summary a rule. The dividend and remainder must have the same signs. In the last example, the remainder is positive and dividend is positive. And in the previous example, the dividend is negative, so we get a negative remainder. So that is the rule when we are trying to do signed divisions. So beside integers, programming language also supports fractions or floating points. For example, pi is 3.14159265 and e is 2.7, and also we have seconds in a nanosecond, and we also can have seconds in a typical century. And we usually use scientific notation to define a floating point. So scientific notation has a single digits to the left of the decimal points. So the definition means a number is scientific notation if it only has a single digits to the left of the decimal point. We have 1.0 times 10 power of -9. This number is a scientific notation. It only has a single digits to the left of this decimal point. And also, this number is also a scientific notation since we have a single digit 3 to the left of this decimal point. But those two numbers are not scientific notation. And if a number in scientific notation has no leading zeros, then this number is called a normalized number. So for example, 1.0 times 10 power -9 is in normalized scientific notation because it does not have leading zeros, but those two numbers are not normalized scientific notation because the first one, it has leading zero, and the second one is not a scientific notation because it does not have a single digits to the left of this decimal point. So we know that we only use binary numbers in hardware, and binary numbers can also be converted in scientific notation. For example, we can have 1.0 into times 2 to the power -1. This binary number is in scientific notation. And such numbers are called floating points. In scientific notation, floating point numbers are represented as single non-zero digits to the left of the binary point. And the format of a floating point in scientific notation is something like that. So we have a single non-zero digits to the left of this binary point, and we have some digits to the right of this binary point, and we also have some exponents based on 2. So this xxx here is called fraction, and this yy here is called exponent. Since we only use binaries in hardware, then we should design a method to represent floating point numbers. So the representation of a MIPS floating point number is shown here, and this floating point is 32-bit long. The first bit, S, is the sign of this floating point. 1 means negative and 0 means positive. Exponent is the value of the 8-bit exponent field. So exponent is yy here. And fraction has 23-bit long. Fraction is xxx here. So that is a format of a MIPS floating point number. If a number applies to this format, then this number is also called single position floating point. In general, floating point numbers have this format. We have S, which is the signed bit, and F is a fraction, E is the exponent. According to this format, exponent is 8-bit, fraction is 23 bits. So therefore, the range of this fraction is like that. This number cannot be smaller than that, and it cannot be bigger than this. Since we only have 8 bits for exponent and we only have 23 bits for fraction, therefore, the smallest number that can be represented in this format is this. And the biggest number that can be represented in this format is set. So we have the range here, but what if we want to represent a number that is bigger than this one? Then we will have overflow. So overflow occurs when the exponent is too large to be represented in the exponent field. So in this format, if the exponent is too big to be represented in this 8-bit, then we will get an overflow. We also may have an underflow. So underflow occurs when the negative exponent is too large to fit in the exponent field. That is underflow. And we talked about this single precision floating point. We also have double precision floating point. The double precision floating point is one way to reduce chances of underflow or overflow. Double precision floating point takes 2 MIPS worth, which is shown here. So instead of 22 bits, the double precision floating point has 64 bits. It takes 2 MIPS worth. And similarly, S is a signed number. Exponent here is changed to 11 bits, and fraction here is changed to 52 bits. Since we change the size of each component, therefore the range of this double precision floating point changes to that. So the smallest number that can be presented in this format is 2.0 times 10 power negative 308, and the biggest number that can be presented in this format is this. And some computers use IEEE 754 format. This format uses a bias of 127 for single precision. So in this format, an exponent of -1 is represented by the bit pattern of the value -1 plus 127, but +1 is represented by 1 plus 127. So this 127 here is a bias. We have to add it to the exponent to get the correct exponent. For double precision, this format uses a bias of 1023. So in this format, bias exponent means that the value represented by floating point number is really this format. So the exponent changes to exponent minus bias. So here is example. If we want to show the IEEE format, if we want to show the IEEE 754 binary representation for the number -0.75 in single and double precision, here is the basic step to get this format. So first of all, -0.75 is equivalent to -3 divided by 4 in decimal, and which is equivalent to -3 divided by 2 to the power 2, since 4 can be represented by 2 to the power 2. And next, we should change this decimal to binary number. So 3 in binary number is 11. Then we get -11 in 2 divided by 2 to the power 2 in 10. Then we can reverse the exponent sign to get -11 based on 2 times 2 to the power -2 based on 10. Then we can translate this format to binary format, and we get -1.1 times 2 to the power -1. Next, I'm going to talk about how we can transfer a decimal number to a binary number. So when converting the absolute value of the number to binary with a fraction part after the binary point, we can convert the integer and fractional parts separately. So for integer part, we can divide the number by 2 recursively until you are left with 0 while taking notes of each remainder. And for fractional parts, we can repeatedly multiply the number by 2 and harvest each 1 bit as it appears left to the decimal. So for example, if we try to convert this decimal number to a binary number, and for this integer part, 29, we can recursively divide by 2. So 29 divided by 2, we get 14, and remainder is 1. We mark the remainder there. And next, we keep divide 14 by 2, then we get a 7, and the remainder is 0. And next, divide 7 by 2 again, then we get quotient 3, and remainder is 1. And 3 divided by 2, we get quotient is 1, and remainder is 1. Then 1 divided by 2, we get quotient is 0, and remainder is 1. Since quotient is 0 now, then we can stop the repetition. Therefore, 29 is converted to 11101. We start from the lower bit, the most significant bit, to the top, which is the least significant bit. And for the fractional part, we can repeatedly multiply by 2. So the fraction part times 2 is 0.8125, and the left side bit is 0. Then we mark 0 here. And that's 0.8125 times 2, then we get 1.625. So the left bit is 1. Then we harvest a 1 here, and then we repeatedly multiply the fraction part. So in here, the fraction part is 0.625. So 0.2625 times 2, we get 1.25. And we harvest the left side, which is 1, and then keep multiplying the fractional part by 2. 0.25 times 2, we get 0.5. And the left side is 0, then we harvest the 0 here. And last 0.5 times 2, we get 1.0. So we harvest 0, and since we reach the fraction part which is 0, then we finish this translation. After we do that, we can convert this decimal number to binary number. So 29 is converted to 11101 because according to this calculation here, 29 is equivalent to 11101. Start from the bottom to the top. And this fractional part is translated to 0110, and we start from the top to the bottom. Next, I'm going to talk about floating point addition. So let's first talk about decimal number addition first. Let's try to add those two numbers in a scientific notation. We assume that it can store only 4 digits of their significand and 2 digits of the exponent. So the first step is we should align the decimal points of the number that has the smaller exponent. So in this case, the second number has a smaller exponent. So the second exponent is smaller than the first exponent. So we should shift this decimal number to left until we get the same exponent. So first of all, we shift this point left, and then we get 10 power 0. And since 10 power 0 is still smaller than the first exponent, then we should do left shift again. Then we get this number which has the same exponent. Since we assume that it can only store 4 digits of the significand, therefore this number changes to 0.016. We can only store 6 digits of the significand. After we get this exponent aligned, then we can add the significand. So 9.99 plus 0.016, we get 10.015. Then the summation is 10.015 times 10 to the power 1. Next step, we should change it to the normalized scientific notation. So recall that the normalized scientific notation only has 1 digit to the left. So we can shift it to the left 1 bit, then we get 1.015. 0.0015 times 10 to the power 2. And also remember that according to the definition, assume it can only store 4 digits of the significand and 2 digits of the exponent, but here we have 5 digits of the significand, then we should round number to 4 digits in the significand. So the final result should be 1.002 times 10 to the power 2. Then let's talk about how we can do the floating point addition. Here is the basic algorithm. So the first step is we should compare the exponents of those two floating point numbers, and we should shift the smaller number to the right until its exponent would match the larger exponent. Then we can add the significance. And third step is we should normalize the summation, either shifting right and incrementing the exponent, or shifting left and decrementing the exponent. Then we check whether there is overflow or underflow. If there's overflow or underflow, then we should give an exception. If no, then we should round the significant to the appropriate number of bits and check is it still normalized. If it's not, then we should go back to step 3 and repeat this process until we get this number normalized. One special step is step 4. In step 4, we need to round the significand to the appropriate number of bits. So how can we round these binary points? Well, for decimal number, if we try to round the bit, and if the number is bigger than 5, then we should add 1. If the number is smaller than 5, then we just ignore this number. And to round floating point numbers, here is the basic strategy. In the default round method, when rounding binary fraction with n-base fractions, so if what is left over is smaller than 1 over 2, then we should round down. And if what is left is bigger than 1 over 2, then we should round up. And if what is left over is equal to 1 over 2, then we have two choices. If the nth bit is 1, then we should round up. But if the n base is 0, then we should round down. So here is an example. If we try to round binary number 1.1011 with 3-bit precisions, so according to this procedure here, so now we are trying to round 1.1011 and we want to round it with 3-bit precisions. Then the precision should be 1.10 and what left over is 11. So 11 is left over. Then we should check whether this leftover number is smaller than 1.2 or is bigger than 1.2. So what left is 11, which is 10.00. If we translate that to decimal number, then we will get 1 times to the power of -1. So the leftover is 11, then which is 0.11 in binary number. And if we want to translate this binary number to decimal number, then we will get 1 times to the power -1 plus 1 times to the power -2, which is 1 divided by 2 plus 1 divided by 4. And clearly this number is bigger than 1 divided by 2. Therefore, according to this rule here, we should round up. So if we try to round this number, according to that, this number is round to 1.11. And if we have binary number 1.1001, and if we try to round this number with 3 bits precisions, so what left over is 01, and translate 01 to this decimal number, then we get 0 times to the power negative 1 plus 1 times to the power negative 2. Then we get 0 plus 1 over 4, which is smaller than 1 over 2. So this number is round to 1.10. And next example is if we try to round this number. If we try to round 1.1010 with 3-bit precisions, then the leftover is 10. So 10 will translate in decimal is 1 times to the power negative 1 plus 0 times to the power negative 2. Then we get 1 over 2 plus 0, which is equal to 1 over 2. Then this case fits the third case here. So if what is left over is equal to 1 over 2, then we should check the nth bit. So if the nth bit is 1, then we should round up. If the nth bit is 0, we should round down. So the nth bit in this case is 0 here. So if the nth bit is 0, then according to this definition, if the nth bit is 0, then we should round down. Then this number is round to 1.10. But if we change it, the nth bit to 1, then since the nth bit is 1, then we should round up. So if we try to round this number, then we get 10.00. So that is the basic procedures to round floating point. Basically, for n base positions, if what left over is smaller than 1 over 2, then we should round down. If the leftover is bigger than 1 over 2, then we should round up. While if the leftover is equal to 1.2, then we should check the nth bit. If the nth bit is 1, then we should round up, which will add 1. If the leftover is 0, then we should round down. And here is a binary floating point addition example. So let's try add numbers 0.5 in decimal and negative 0.4375 10 in binary using the floating point addition algorithm, and assume the position is 4 bits and 3 bits right of the binary point. Alright, so I will do this example here. So if we trying to add those two numbers in a binary format, then we should first translate those decimal numbers to binary numbers. And recall that we use this strategy to translate decimal number to binary number. So in this case, we need to translate 0.5, the fraction part, to binary number. So we should repeatedly multiply this fraction part by 2. So 0.5 times 2 equal to 1.0. Then we should harvest the left side bit, which is 1. And since the fraction part is 0 now, therefore we finished this process. So 0.5 in decimal is translated to binary number, which is 0.1 in binary. So 0.5 in decimal is translated to 0.1 in binary. And next, we should translate the second number into binary, and we should still apply the same method here. So the fraction part is 4375. 4375 times 2, we get 0.4375 times 2, we get 0.875. Since the left bit is 0, then we should put 0 here. And next, 0.75 times 2, then we get 1.075. 0.75. Since the left side is 1, then we should 1 here. And the fraction part is 0.7500 times 2, which is 1.5. And we'll put 1 here. 0.5 times 2 is 1.0, and put 1 there. Since the fraction part is 0, then we can stop this process. Then this decimal number is translated to negative 0.0111 in binary. After we get it translated, we should also change it to a scientific notation. 0.1 is changed to 1.0 times to the power of negative 1. And the second binary number can be translated to 1.11 times to the power of negative 2. After we translate those two decimal numbers into binary number in scientific notation, then we can do the floating point addition. So the first step is to compare the exponent of those two numbers and shift the smaller number to the right until its exponent would match the larger exponent. So the first step is compare the exponent. We should shift the smaller number to the right. Then we will get shift it to right 0.111 times to the power of negative 1. Therefore, we get this exponent matched. Then we can do the second step. The second step is add the significand. The second step is add this significand. So the first significand is 1.0, and the second significand is 0.111. But remember that this number is negative, so it should be negative 0.111. Then we'll get 0.001. And this exponent is to the power negative 1. That is the result after the second step. So the third step is normalize the summation. Either shift right, increment the exponent, or shift left and decrement the exponent. So recall that normalized means a number in a scientific notation that has no leading zeros. It must have 1 here in the left side of this point. So we should normalize the summation. Third step is normalize the summation, and first we get the summation is that we should normalize it. So we should do shift left and decrement the exponent. So we first shift left 1 bit and decrement the number, and since the left side is still not a 1, then we should do shift again. After shifting, since it is still not a 0, then we should do a shift 1 more time. Now we have it. Now we have this normalized number. So the normalized number means the left side digits must be a 1. It has no leading zeros. And next we should check whether there's overflow or underflow. So we have a really small exponent, therefore there's no overflow and underflow. Then we should round the significand to the appropriate number of bits. So the first step is to round the number to the appropriate number of bits. So remember that since we assume the position is 4 bits and 3 bits right the boundary point, and since the fraction part is 0, so there's no necessary to round it, then we can get the final result, which is 1.000 times to the power negative 4. That will be the final result of this example. I also post the steps in the slides, and you can also check that. And here is another example. Let's try to add those 2 decimal numbers in a binary using the floating point addition algorithm, and assume that the position is 8 bits and 7 bits right of the boundary point. So to do that, here is the answer. We need first to translate those two decimal numbers into binary number by using the method we talked about before, and then we can do the algorithm. Step 1 is to analyze the exponent. We shift it to the right and make the exponent the same. So 2 to the power 1 is a small exponent. We should shift the whole number to right and make the same exponent. After we have the same exponent, then we can do the summation. So those two numbers, after we add the two numbers, we get this one. And step 3, we should normalize this summation. Since it has leading zeros, then we should shift this number to left and decrease the exponent. Then we get 1.11 times to the power 2. And step 4 is round those number. Since the remaining number is all zeros and it requires 7 bits right of this boundary point, and then the final result of this question should be 1.11 times to the power 2. To double check whether we get the correct result, we can translate this binary number into a decimal number. And 1.11 times to the power 2 is 111, which is 7. So we can see that the result we get is 7, but actually 3.133 minus 2.37 should be 6.96. So we did not get a really accurate result. So the reason is that we assume the precision is 8-bit, we ignored some bits here, and that's why we did not get a really accurate result. So if the system is 8-bit, then we will get an inaccurate result. Right now, almost every system is 64 bits, then we should get a more accurate result. Next, I'm going to talk about floating point multiplication. So before we move to floating point, let's talk about decimal numbers. Let's try to multiply some decimal numbers. So here is an example. Let's try to calculate the multiplication of those two decimal numbers and assume it can only store only 4 digits of the significand and 2 digits of the exponent and 3 digits to the right of this decimal point. The first step to calculate this multiplication on decimal numbers, we can calculate the exponent of the product by simply add the exponent of the operands together. So we have 2 operands, we have 10 and -5. We can just simply add them together, then 10 plus -5, we get 5. Then the new exponent is 5. Next, we can multiply the significand. So 1.10 times 9.200. Then we get this final result. Since we have 3 bits of fraction number and we also have 3 bits of fraction number, so we should add the point here, which is move 6 bits from the right side. So 1, 2, 3, 4, 5, 6. And that should be the result by multiplying the significand. After we get this significand, then we can combine it with exponent, and then we get this result. And the next step is normalize the product. So we can see that this number is not normalized because it is not in scientific notation, only have one single digit, the right side of this decimal point. So we should shift this to right and increment this exponent. So we get 1.0212 times 10 to the power 6. And in the end, we should round the number to 4 digits in the significand, because in the beginning of this question, we assume that 3 digits to the right of this decimal point. So we only allowed 3 digits to the right of this decimal point. Then we should round this number, and in the end, we get this final result, which is 1.021 times 10 to the power 6. So based on those procedures, we can talk about this floating point multiplication algorithm. So similarly, the first step is to add the base exponent of the two numbers and subtracting the base from the sum to get the new base exponent. And next, we can multiply the significand, and then we can normalize the product if necessary by shifting it right and increment the exponent. Then we should check whether there's overflow and underflow. If there's no overflow and underflow, then we should round the significand to the appropriate number of bits and check whether the result is normalized. If it is normalized, then we move to the final step, which is set the sign of the product to positive if the signs of the original operands are the same. If they differ, then we should make a negative sign. So to have a better understanding of this algorithm, let's talk about this example. In this example, we are trying to multiply two decimal numbers using the floating point multiplication algorithm. And we also assume that the position is 4 bits, which means we only allowed 3 bits right of this binary point. So first of all, we should first convert those two decimal numbers to binary numbers. And we already did that before. And step 1 is adding the exponent without base. And those two exponents is -1 and -2. So -1 plus -2 is -3. Or in some system we use base, then the result should be 124. And next is to multiply the significand. So we should do something like that. And since we have 6 digits of fractional number, so we should mark this point and make it has 6 bits of fractional numbers. And according to the first step, we get the exponent, which is -3. Then we get the result, which is 1.110 times to the power of -3. So since it requires 4 bits and 3 bits right of this point, so that is the result after step 2. And step 3 is now we check the product to make sure that it is normalized. So this format is already normalized since we only have 1 bit in the left side of this point. And if this product is normalized, then we should check whether there's overflow and underflow. So because -3 is inside this range, therefore there's no overflow and underflow. And step 4, we should round the product. And since we already fit into these 4-bit limitations, then there's no necessary to round this number. Step 4 does not make any change. And in step 5, since the signs of these original operands differ, so we should make the sign of the product negative. Hence, the final result should be -1.110 times to the power -3. Here is another example. Try multiplying those two decimal numbers using the floating point multiplication algorithm and assume the position is 4 bits, which means we only allowed 3 bits right of this binary point. And while the first step, we should translate those decimal numbers into binary number. And then we can add the exponent. So exponent is 0 and 1, then 0 plus 1 is 1. And next step, we should multiply the significand. So 1.101 times 1.001, and we get 1.11001 times to the power 1. To the power 1 is exponent we get from step 1. And since the position is 4 bits, we only allowed 3 bits right of this binary point. Therefore, we get this result after step 2. We only allowed 3 bits right of this binary point. Next, we should check whether there's overflow and underflow. Since 1 fit in this range, therefore there's no overflow and underflow. And since there's only 1 bit left of this point, therefore this number is normalized. And step 4 does not make any change. We does not need to round this number. So step 5, we should sign the product. since those two numbers has different sign, therefore we should make this number negative. The result is negative 1.11 times 2 to the power 1. So to check the accuracy of this algorithm, we can translate this binary number into decimal number. So after we do the translation, we get the final result, which is negative 3.5. So clearly, 1.63 times negative 2.37 is not 3.5. So the result is not really accurate. The reason is because we only assume the position is 4 bits. We only allowed 3 bits right of this binary point. So for example, in step 2, we ignore the last one here. And since the last one is ignored, and we does not get accurate result. So for exercise, I want you to redo this example and using the same two decimal numbers, but this time we assume that the position is 7, so it allows 6 bits right of this binary point. So in the end, you should get a more accurate result than the previous one. So please try to do a little bit of practice and upload your answer to Blackboard. And that's all for this video. Thank you for watching.